Welcome everyone to our third keynote talk of the day and of the conference as well. And this time will be given by Ajay Vinze, whose research focuses on topics ranging from big data analytics to collaborative computing and disruptive innovation. His talk will cover in broad strokes the building blocks, facilitators and challenges for big data-based decision making. So without further ado, please give a round of applause for our next keynote speaker.
Thank you.
Reminder to ask your questions through the link dsc.network/Q/A/Tesla with a capital T. Thank you.
Well, good afternoon. Dobar dan. Good? All right. Well, my name is Ajay Vinze, and I'm delighted to be here. I want to thank the organizers of this conference for inviting me here. Alexander, Meena, and others have done a wonderful job in making sure I got here in time, and B, that they've organized a wonderful set of people to have a good conversation about data science. I've been listening to the presentations all morning, and it's been interesting about the common themes that come up. How do you define data science? What is data science? Where's the value in data science? Is there a return on investment from data science? So I'll try and see if we can address some of those questions. I don't think we'll address all of them, but we'll try and see if we can address some of these questions. And I'd like to start by positing that, data science by itself is a little bit of a misnomer if you think about it. And I'll jokingly say this because you're all data scientists, so I don't want to offend anybody, but any discipline that attaches the word science to it is not really science. Right? The real science is biology, chemistry, physics, and so on. Social science, computer science, data science. I say this in jest because I'm a computer scientist also, but so I can get away with that. But I'm a professor of information systems. I'm the dean of the Trulaske College of Business at the University of Missouri. Have been, I consider, a data scientist for the last 30 years. But of course, they didn't call it data science at that time. So what I'm going to talk to you about is how do we use data riches and try to define what kinds of challenges we have in front of us. And then I'll try to reflect on those challenges through two projects that I've been involved in over the years in two very dissimilar disciplines. One in the area of semiconductor manufacturing and the other area of public health and disease management. So completely different orientations. But before I get started, I want to at least talk to you a little bit about what we are up against. Now, when you look at data science or technology or any kind of change that's going on, one of my areas of interest is always looking at disruptive innovation. I think of it as a long-distance hurdle race, okay? And I understand Serbians are particularly interested in athletics, so I thought I'd start off with this kind of an experience. So if you think of a long-distance athletic race, hurdle race, the first hurdle that we have is this notion of innovation, technology, and I'll put data in there as well. So those are the three things you want to look at. And as any good athlete would tell you, you take a little bit of a run up here and jump over this first hurdle. You need a little run up before you can jump over that first one. But assuming you clear that, and we'll come to this data business in just a second, but assuming you clear that, this is what is waiting right in front of you. Okay? And understand this distance is meaningful. If this is not enough, you're going to see a nice face print over there. So this notion of how do you set organizations, management, and culture to accept innovation, technology, and data changes is a critical question. And assuming we even clear that, and right behind that is this. Okay? So no easy answers, but plenty of interesting situations. But this is sort of what we are up against in the world as today's manager, today's educator, today's whoever we want to call ourselves. Okay? This is the world we are in. Earlier today, they had an interview, and the interviewer asked me, well, what do you think about how far behind is so-and-so in data science or what have you? My standard answer is no country can be more than 20 years behind in any technology, because once a child is born, it takes 20 years to get up to where they're productive. So you can't be more than 20 years behind ever. So this notion of saying we're 50 years behind or 30 years behind is nonsensical. It doesn't bear with the data. So given this situation, here's what people talk about in terms of data riches. First thing people talk about is big data, right? Big data, everybody's talking about it. It's on the cover of Time magazine, The Economist, Popular Science, Harvard Business Review. It's all over the place. Everybody's talking about this, right? So we all believe big data is really king or queen, whatever you want to call it, right? Yes? I'll give you an opposing viewpoint. And understand, I come from the University of Missouri. We are in the center of the United States. It's a land grant university. It's one of the top 6 land grant universities in the US, given the AAU status, but very agriculture focused also. So I'll give you an example of what the other side thinks of big data. And the cow is symbolic of where I'm coming from. But I'd ask you to pay attention to the letters over here. So not everybody is buying this business of big data. People are consider these kinds of things as troublesome parts of big data. Okay? So big data is important, but big data doesn't come without its own troubles. So given this situation, let's think of what data is and what data riches are. So if you think of this, this is the acceleration that's going on. This whole notion of large amounts of data and data coming at us at a very fast pace became more pronounced after the internet. It was always there. I mean, there's always data, there's always big data, there's always this notion of plenty of data dealing, but it became pronounced since the 1980s, and more so in the 90s and then 2000s. But then you start seeing this acceleration. This is like a roller coaster ride, right? You're seeing picking up steam. There you go, big data analytics. This is all technology evolution over here. Technology is making it better and better. And then what you do is, in addition to technology, you add innovation accelerators to big data. And then you start seeing 3D printing, renewable energy, IoT, cognitive systems, nanotechnology. You see that speed picking up for big data, right? And once you come out on this side, this is where the value comes up from big data. So you have to pick up enough speed to go up the value chain in some meaningful way. And that's where you're going to see value coming up over here from smart grid, connected cars, smart homes, AI, and narrowly focused AI orientation, smart cities, next generation, education, connected healthcare, and you can go on and on and on over there. That's sort of, if you want to think about it, data as the accelerator. So when you say data riches, big data, that's what you're really thinking of. Here's a little perspective on how much data is being generated. Every minute of every day in 2018. Take a look at it. Amazon ships 1,111 packages every minute of every day, nonstop. On the other side, you can see all kinds of other details over here. There's 12,986,111 texts sent every minute of every day. Each one of this is a data point of different source. So when you say big data and big data riches, this is what the data is that's being generated. In fact, there's more data generated in the last 18 months than there were in the last 5,000 years of humankind. Think about it for a second. So we are not swimming in data, we are drowning in data. That being the case, the question becomes, why focus on data? And this is always an interesting balancing act. So I'm in the business school, and my background is kind of curious. I started as an accounting person, then became a finance master's. My PhD is in computer science. So I went in reverse gear in some ways, sort of found my way back into. So this is always, so in business, they always talk about having the good business instinct, having the good business judgment, what have you. That's this end of the spectrum. And as they say, everybody can have their opinions, but not everybody can have their data, right? So the whole idea in business is how do you make the right decisions? How do you balance this data and opinion kind of instinct orientation? So the role of data is really trying to make sure this thing doesn't tilt in this direction. That is, you make in the absence of good data, in the absence of useful data, what happens is opinions take over. And this is what happens when opinions take over. And this is what we say, in the absence of data, business decisions are often made by the hippo. And the goal of data scientists is to avoid the hippo. What in the world is a hippo? Anyone know? Hippo stands for the highest paid person's opinion. Not always the right opinion. Think about it in your own company or in your own organizations. When you really get into a conversation and when you get into some kinds of arguments, whose opinion counts the most? Who's around the table? But if you have this at your disposal, you have a counterpoint to that. Okay? So you're trying to avoid the hippo in most cases. So what I'd suggest to you is think about this thing. There's really a trifecta of three things going on. This is a unique storm. Data science has become popular because there are three unique things that have happened at the same time. Each one of these were following their own trajectory over a period of time. They were all following different trains of time. Computing power has been growing. You have the Moore's law going on for the last God knows how long, right? And understandably will stay on that same path for a while. But you have tremendous processing speeds, you have great powerful workstations, parallel computing, all this is going on. So you're building up computing horsepower. Why are you building up this computing horsepower? Because you have increasingly specialized your data gathering abilities. And if you look at just Fortune 500 companies, in 1993, you just had 8% of Fortune 500 companies that were actively gathering data as a data warehouse. In 2015, 100%. And now it's much more, you can't be more than 100%, but now it's not just the Fortune 500 companies, it's going down to mid and small size companies as well. So this is where you are. And then simultaneously on the side, you had these strange set of algorithms or parameters or techniques that were being developed, some in statistics, some in AI, okay, where you're looking at pattern matching process. In statistics, what you're really looking at is the notion of probability. That is, if I repeat it again and again and again, then as n approaches infinity, how close do I get to correcting the answer? In AI, what you're trying to find is how do you satisfy in a given pattern match setting? How could I do something? But you have these three different forces simultaneously coming, and that's really what data analytics or data science, that's the nexus of data science. Okay, so if that's the nexus of data science, then we need to let's look at each one of these computing power data and just think about them for just a second. I don't know if some of you have seen this chart. This is, I picked it right out of Time magazine, so it's from 2011. Okay, this is by Ray Kurzweil, who's a futurist, and he's been making predictions for a while. This is a phenomenal, this shows you the exponential growth of computing power. If you look at the timeline over here, we have just surpassed, in global computing power, we surpassed the brain power of a mouse. Okay, but if you keep up with Moore's law like you are, by 2045, what they're saying is you will have singularity. That is, you will not be able to distinguish man and machine. That is the 2045, very much, maybe not within my lifetime, but certainly in lots of your lifetimes. This is the time where in 2045, they claim that the total amount of computing power in the world will overshadow the total amount of brain power, human brain power in the world. This is scary stuff. When they say, be scared of AI, it's coming one way or the other, whether you like it or not. Okay, so it's something worth looking at. With AI, what did we do? Oops, I'm going the wrong direction. With AI, what you started off with this segment of structured intelligence, if you will, around games and simulations and so on. And now we have progressed through IBM Watson, which is phenomenal. If you haven't played with it, please do go play with it. It's just unreal what it can do. And you're going further and further into deep learning. So now you're trying to really see how I can squeeze the most I can out of data. It's more than just making some predictions. It's much more than that. And the third one is this notion of just data sizes. So databases today can range into exabytes, and that's one with a lot of zeros. And the general hunch is if you have so much data, then even though your statistics professor taught you that correlation doesn't mean causation, by golly, if I see it so many times happening at the same time, pay attention to it, okay? So the largeness of size of data causes certain amount of ability for you to read into this data that you can read. So my strong hunch is that there is some information in this data. Now, this, by the way, this notion of having this hunch that there's something, this is not a new idea. Jacob Bernoulli came up with this notion in 1713. So this notion of big data is not that new, okay? He had this law of large numbers, and he published it over here. And in his writing, it was described that he described a law of large numbers as a principle so simple that even the stupidest man instinctively knows it's true. However, the power of mathematics, it took an academia. It took him 20 years to develop a rigorous mathematical proof to prove that, which he claims the stupidest man should have known instinctively. It's interesting. Simple example of law of large numbers. This is even if you're just rolling a dice. If you roll it, it has 1 through 6 on it. On average, you should get 3.5. Just by doing about 1,000 runs of it, just see how close you come to the mean, how quickly you regress to the mean. If I do this 1 billion times, it'll be like a perfect straight line. Okay? It gives you some sense of what big data and implications are therefrom. Okay. So when you talk about data, I would suggest don't just focus on the bigness of the data. The bigness is certainly important. Big data is important. So volume of data is important. And they talk about the volume of data over here. You talk about enterprises are awash in all types of data, 12 terabytes of tweets to find sentiment analysis and so on. You can think of those. That's certainly possible. But along with the volume of data, you have to think about 3 other V's related to big data. The second V you want to think about is the velocity, the speed at which data is coming at you. It's not just that a large amount of data is coming at you, it's the speed at which it's coming at you is also changing, okay? Typically, when you're talking about fraud, and I'll give you some business examples. So when you're talking about fraud analysis or something, it is not enough to have anything less than a 5-second response rate to find that there's fraud in a credit card charge, okay? That's typically the norm. When you're looking at the fintech industry, the financial technology industry, which really focuses on arbitrage and so on, in the fintech industry, they've actually laid fiber optic cable from Chicago to New York because a millisecond difference, everyone understands arbitrage, right? So there are 2 different stock exchanges. If a stock price is one in New York Stock Exchange and a different one in Chicago, even if the stock price difference is 1/100th of a cent, and if I know that difference, less than a millisecond before anyone else, I can make a killing in the market. Every single time. Doesn't take genius. All you need is that information, and you need there's in fact a company that has been built just on that. It's called TradeBot. That has not lost money for the last 48 quarters. Never. Okay? And all they have done is trade on arbitrage. This is the financial technology industry, fintech industry is based on this. The speed at which you get the big data. So, one of our esteemed colleagues earlier today, Sasha, was talking about show us examples. Well, here are some examples. These are real things that are going on. Also, variety of data. So the variety of data has also changed. You get structured data, you get unstructured data, you get sensor data, audio data, video data, clickstream, logs. All this, they're different types of data. Our very first keynote this morning was showing us 4 different aspects in R, how you deal with them. Well, deal with that in this context. Causes a level of complexity much more than anything you can imagine. And then the last one is just as important, the veracity of data or the value of data. The concern, they're really talking about data integrity. And the issue is, and this is a scary statistic for me as a business school person, that 1 out of 3 business leaders don't believe or trust the information they get, the data that they get to make their decisions. So big data presents them with a huge concern and a huge opportunity. So I'm going to talk about 2 projects. Let's see how much time I have, 15 minutes. Okay. I'm going to talk about 2 projects, and I'll give you the punchline ahead of time for these projects. The first punchline is to get data is easy, to get the right data is very difficult. Okay? Think of that for a second. And I've written these down very easily. It took me 18 years to figure this out. So clearly, I'm a little slower than you are in terms of smarts. But the other big insight I learned from these projects, and by the way, all my research is always applied, so it always is done in an industry context for the last 30 years. So it always has a direct. The second insight I got from data was to get insights is easy. But to translate those insights into decisions that make sense is very difficult. Okay? By the way, both these projects in terms of return on investment, this one had, I'll give you the numbers in a second, but let me talk about the projects first. But they're in millions, the return on investment on both of these projects. So the 2 projects I want to talk to you about, the first one is called FAFI, and I won't mention the name of the company I work with, but I'm sure you'll be able to guess it, but I'll leave that alone. This stands for Failure Analysis, Failure Identification. I'll tell you the industry. This is semiconductor industry that manufactures chips. Okay, and this. So we'll talk about finding data in this context. The other project that I'll talk to you about is something that I did with the Department of Public Health in Arizona, where we are really trying to find out how do you control disease propagation in populations with non-pharma intervention. That is, without using medicines and vaccines. Just by changing policy, how do you actually control disease propagation in population? It's a huge thing in terms of value back for the state and the country. Okay. So let me start off with the first one. Just to give you a sense of the project that we are working on. This is failure analysis, failure identification. This is in a chip manufacturing business. They typically are working currently at the 22 nanometer scale, right? So nanometer, just so you know how small a nanometer is, it's very small. But if you take a strand of your hair and divide it into 1,000 parts, that's a nanometer. The width of the hair. That's a nanometer. That's the size of a gate, of a logic gate on your chip that sits in your machine. Okay, so what happens is when you're, and this tells you at the scale at which so they're deploying at the 22 nanometer, but they're now working in research at the 5 nanometer scale. At this scale, if even you have the slightest gyration, in fact, if you look at a clean room that these chips are manufactured in, they're 1,000 times cleaner than the surgical rooms in which you do open heart surgery. Because at that scale, you can't afford even the slightest speck of dirt in the air. Because if you do, it looks like a rock when you look at the nanometer scale. So they do all kinds of testing. So this company had been collecting this data, and they do electrical tests, chemical tests, air quality tests, wave tests. They do all kinds of tests to see if any gyration is affecting the batch that is being manufactured. And just so you know, if one batch goes wrong for this company, it is a direct hit of $5 million to the bottom line of the company, not the top line. Okay? So these are significant things. And they had been collecting this data for over 20 years. Now the problem was they were collecting this data, and I've given you an example of one of the ways in which they were collecting the data. It's called the transmission electron microscope. That's how they're sensing this. And they're storing this stuff day after day. Problem is, they have all this data, they can't find the data. If they and for doing one of these tests, it typically costs them $100,000 to do a particular test. And what they found was they're spending more than $100,000 trying to find old results that they used to just redo the test and store the new results one more time. So the data was growing at some crazy rates, right? So this is the time as an academic I was called in to talk to the senior management over here. And it took me a little while, but then what I figured was, this is the same problem as what we do in a conference like this. You meet a lot of people, you exchange business cards, and you promptly go back and you put those business cards in your Rolodex, right? Do you remember the names of the people you met? Do you remember them you stored them by the last name, right, in your Rolodex? How do you remember these people? Well, you remember them in a strange way. Well, I was having lunch with this person, or we were drinking coffee, someone came from the back, bumped into me, I dropped coffee on myself. I want that person. How the heck do you figure that out? And what technique do you? So the issue always is the way you store data and the way you retrieve data is exactly the same these days. But really what you want it to be is the way you store data is one way, but the way you want to retrieve it is quite another. How do you do that? And that was the challenge of this company. And we spent 18 months working with this company on this. And what we did was something like this. And you say, what the heck is that? Well, what it is really creating what is called an ontology. That is, you create multiple structures around how you store the data. So normally you store data in one way. So this is just one example over here. Store data by content or by domain, and you have all these other characteristics. But then you cross-connect each one of them in every single way. So what was taking them close to between 3 weeks to 4 weeks to find the data, we reduced that time from 3 to 4 weeks to under a day. And then we are continuing to work on that. It has to be a sub-hour return on. This has real implications for this company in terms of real dollars. Every test that they had to redo is $100,000. And they do that often. Because if you miss one test, it's a $5 million to your bottom line. So these are real simple numbers if you think about it. Here's another project that we were working with. This is a public health project. What we were looking at is how do you deal with disease propagation when diseases get into, and we are talking about communicable diseases. So diseases not that you can't pass. These are all diseases that can be passed from one human being to another through contact. And the Centers for Disease Control, who funded part of my research, there's a database of 56 such diseases that they track in the United States that are communicable. And each disease, by the way, has a model. So there's epidemiological models over there called SEIR that says for any disease, a disease has a normal life cycle, how the virus behaves, and how it propagates in the population has a life cycle. That is, some set of population is susceptible to that disease, then they're exposed, then they may or may not get infected, and then they may or may not recover, and they may or may not live. Okay, so these are real issues. And these are big issues that we were dealing with. We were dealing with it principally initially in the realm of H1N1, and as H1N1 was propagating in a big way. And what we were doing was using this model to actually design a way in which you can most efficiently create policy to distribute vaccine to maximize saving life. This project, by the way, the first project, the company said they were on average was giving us about $5 million of saving on a regular basis. This project, the state of Arizona published this. They say it saved over $50 million in 1 year. Does data riches have impact? Absolutely. Okay, there's no question about it. What did we do over here? We actually gathered data from all these different sources in an attempt to surveil those diseases, create these investigative follow-ups, and then see these observed events and push it back. I'll give you an example. This is sort of a sample thing. So we've set it up that, again, by the way, the data I have is only for Arizona, California, and Mexico. That's the only. I didn't have the computing horsepower in my lab to handle more than that. I have plenty of companies running behind us trying to tell us how they can fund this in order to commercialize it. But what you are doing is you're defining what the disease is, and you're saying, if this disease, this over here, I'm showing you, these are the, if you will, 16 different quadrants around Arizona, California, and Mexico. I can start the disease in any propagation. This is agent-based simulation is what we are doing. You use repast, and really every dot that you see over here represents 10,000 people. And they actually move. And when they move and touch each other, they have a particular contact, and they move differently during the day as they do in the evening and during the nights and so on. So it's a very close simulation using big data. But again, the idea is that in a very different context, think about it. One is semiconductor industry manufacturing, the other one is public health. Nothing to do with each other than the fact that they use data in a particular way. So when you move from these kinds of projects, as you push forward, and it's interesting, you have data science 4.0. People in academia are currently talking about enterprise 4.0 as well. That is the fourth generation of enterprises that are defined by information technology. And what the drive is as follows, and I won't go through all of this in great detail, but they're talking about how these are the enablers: systems, intelligence, process management, leadership, people. And it talks about how with technology these have changed from enterprise 1 to enterprise 3. This is sort of where the state of the art is today. This is where we are going. Data is just going to dominate everything on all different scales over here. Now, if that's the case, and since I'm running out of time over here, I thought I'd end with, with data you can make all kinds of magic. So I'll start with a magic trick here. Right? So take a look at these cards. Right? Lots of people in the room over here. I want you to mentally select one card. Okay? Don't tell the person next to you. Careful now. Select one card, remember it. All okay? Whisper it to yourself, not to the person next to you. Your card's missing? Very simple trick, right? You change all the cards. But here's the lesson to be taken away from this. The lesson over here is when you're dealing with data, be careful and listen carefully to the question that's being asked. The question I asked you, or what I suggest, is pick a card and remember that card. What was I really telling you? Forget all the other cards. And so when I replaced all of them, it looks like I did magic. Data science, data analytics is very much like magic of this sort. We have to be careful what questions we ask, and more importantly, we have to be careful what assumptions and justifications we make about that data. All right? Thank you very much. You've been a wonderful audience.
Thank you, Ajay. We have time for some quick questions, so just a quick reminder to ask your questions via the link here. So it's dsc.network/Q/A/Tesla with a capital T. So with regards to the public health project, we have a question here. So did you save money, lives, or both?
Both. Money and lives. In fact, we had to go through an elaborate process of defining what the value of life is. And that's a very tricky question by itself. When you say, well, everyone values their life much more than anyone else could, right? We get that. But in fact, in industry, there are actuary tables that tell you what the productive value of an individual. So a person like me who's clearly getting old over here, his value is much lower than someone in their 20s and 30s who have a very productive life. And depends on the type of education they've had. It depends on what kind of work they're doing. So you have to factor in. It was a very complex equation we had to go through. We worked closely with insurance companies and with the state and national government to actually figure out the demographic data and the cost value. There's a lot of criticisms we got by that. Some social groups said, how dare you put value on life and this and that. And I said, what do I know? I'm just an academic. I just do this kind of work. But it really is a tricky thing. But there is a way. Insurance companies have been doing this all the time. How do they come up with your life insurance premium? That's exactly how they do it. So it's not rocket science, but it is when you start doing it in a public good, it's a tricky question. But yes, money and lives both.
In your presentation, you mentioned Enterprise 4. So how does Enterprise 4 actually influence current people in the job market? And can they adjust in time to not be replaced with computers and, as you saw there, with future automation?
My suggestion to everybody over here would be, and clearly over here people are much smarter than I am, but my suggestion would be, when you're looking at data, data is, if you will, the lifeblood of organizations these days. So anything you can do with data, whether it's storage, retrieval, access, analytics, pattern matching, what have you, anything you can do with data is going to have you in good stead. That's really what it's all about. If I can just give one example, think about this. What is happening? This is the professor in me coming out, so can I have 10 seconds?
Sure. Go for it.
If you think about it, from 1858 to about 1970s, or 1980s even, it was the world of aggregation. So the way you became big and powerful in companies and in business was you aggregate and you became bigger and bigger and bigger. So bigger the company, the more powerful the company and so on, right? So that's why the multinational is a global corporation. Think about today. Which is the largest retailing company in the world by revenue? Amazon. Does it have any inventory of its own? Largest hoteling company? Airbnb. Does it have a single hotel to its name? Largest mass transit company in the world? Uber. Does it own any cars of its own? You notice a trend here? What you're getting is a disaggregation of large companies. So as academics, this is the kind of work we need to be doing. Industry is always focused on the next quarter. As academics, we have the luxury of thinking 5 years ahead of industry. That is our job, okay? So when you say what should you train at, you should train on data of every form, because what you're seeing is a disaggregation of organizations, and you're seeing value being created at every part of that value chain. That's why Uber, Airbnb, and Amazon do as well as they do. And you're seeing the same kind of thing in just about every industry out there today.
Thank you. It's quite an elaborate answer to an elaborate question. So going into a bit more technical stuff, do you use any process models like CRISP-DM for data science projects?
That's a good question. I prefer not to talk about specific models. I'm not wed to any model. I'm not wed to any language. I'm not wed to any platform. I'm completely technology agnostic. You give me the problem first. I'll figure out what technology I'm going to bring to bear to it. So I think many times we overemphasize that I'm an R programmer, a Python programmer, or I'm technology X, or I'm a process modeler of certain. To me, that is not interesting. To me, what's interesting is, can you define the question carefully? And I think we are all individually and separately smart enough that you can pick up whatever technology and model that needs to. So I've almost never identified myself with a language or with a particular platform. So, long way of saying no.
A long but a very good way, and a good way to, I think, conclude this talk. So I would like to thank you once again for giving this keynote talk, and on behalf of the conference, I also want to give you the certificate of appreciation.
Thank you very much.
I hope you enjoyed it.
Let's see. Thank you.
Thank you.